concept of a basis and coordinates is pretty important in linear algebra. The idea of a basis is that each vector of a vector space can be written as a unique linear combination of some basis vectors. The unique coefficients in the representation are called the coordinates of the vector with respect to the basis. Okay, let's take a closer look at the basis representation and coordinates of vectors. Let capital V be some vector space over a field K. And let B is equal to B1 to Bn be a basis of this vector space V. Having a basis B of a vector space V means that each vector in the vector space can be written as a unique linear combination of the basis vectors B1 to Bn. So let small v be some vector in the vector space capital V. Then small v can be written as a unique linear combination of B1 to Bn. That means V is equal to S1 times B1 plus S2 times B2 and so on plus Sn times Bn. The S1 to Sn are elements of the field K and they are uniquely determined. What does unique in this case mean? It means that if you had another representation of small v as a linear combination of the basis vectors B1 to Bn, for example, like that here, v is equal to x1 times b1 plus and so on plus xn times bn, it would immediately follow that these new coefficients here, x1 to xn, have to be the same as the old ones, s1 to sn. That means x1 has to be equal to s1 and so on until xn has to be equal to sn. This is what unique means in this case. There is only one way to write down v in a linear combination of the b1 to bn by using these particular coefficients s1 to sn. So the s1 to sn are uniquely determined. These uniquely determined coefficients s1 to sn are also called coordinates of the vector small v with respect to the basis b. Usually you put these coefficients s1 to sn in a vector like that. So this here is the vector that has s1 to sn as entries. It's an element of Kn, because s1 to sn are elements of the field K. This vector that contains the coordinates s1 to sn is also called coordinate vector of small v with respect to the basis b. The notation is like that. So the coordinate vector of v with respect to the basis b is this vector here. So that here is the notation for the coordinate vector of a vector v with respect to the basis b. Let's take a look at an example now. Let our vector space v be equal to R2. Over the field K is equal to R. Our basis b is equal to 0, 1 and 1, 1. So this here is b1 and this here is b2. Why is this a basis of R2? Because the dimension of R2 is 2. We know that two linear independent vectors form a basis, and these two vectors, b1 and b2, are linear independent, so B is a basis. Now we take small v is equal to 2, 1 from R2 and want to find the coordinates of small v with respect to the basis B. So we have to find the numbers s1 and s2 so that small v is equal to 2, 1 is equal to s1 times 1, 0, 1, 0 is the vector b1, plus s2 times 1, 1 and 1, 1 is the vector b2. We can also write this down by using a matrix. Then this looks like that here. Now you have to solve this linear equation system for s1 and s2. You can use any approach you want to solve that system. For example, the Gaussian elimination method or my cross-product approach. In this case, I will solve the system directly because it's a pretty easy system. Okay, so from the second line here, we get that s2 has to be equal to 1. Now we can insert this here in the first line and get that s1 plus 1 has to be equal to 2. From this we get that s1 is equal to 1. So in the end we get that s1 has to be equal 1 and s2 is equal to 1, 2. So the coordinate vector of the vector 2, 1 with respect to the basis B, so this basis here, is the vector s1, s2, and this is equal to 1, 1. So this here is the coordinate vector of the vector 2, 1 with respect to the basis B. Let's take a look at another example now. Our vector space V is equal to Kn over the field K. Our basis E is the standard basis of Kn. It looks like this here. So the first vector in the basis is E1. It looks like that. All the entries of this vector are 0 apart from the first entry, which is a 1. The second vector in the basis is E2. All the entries of this vector are 0 apart from the second entry, which is a 1. And the last vector in the basis is called En, and it looks like that here. All the entries are 0 apart from the last entry, which is a 1. So this here is the so-called standard basis of Kn. Now let's take some vector x from the vector space Kn. This vector x looks like that. So here you have the entries x1, x2 and so on until xn. Now the coordinate vector of this vector x with respect to the standard basis is equal to x itself. Why is this the case? Because you can write x the following way. x1 times e1, the first vector in the standard basis, plus x2 times e2, the second vector in the standard basis, and so on, plus xn times en, the last vector in the standard basis. Now these numbers here, x1 to xn, are the coordinates of the vector x with respect to the standard basis. But these numbers here, x1 to xn, are the entries of the vector x. So it follows that the coordinate vector of x with respect to the standard basis is the vector x itself. Okay, let's take a look at some properties of the coordinate vector with respect to a basis b. We have the following result. Let V be a vector space of dimension n over a field K. And let B be a basis of this vector space V. Let F be the function from the space V to Kn that assigns to each vector small v its coordinate vector with respect to the basis B. So f is the function that assigns to each vector small v its coordinate vector with respect to the basis B. Then f is an isomorphism. An isomorphism is a function which is linear and bijective. What does that mean? So first of all, it means that each vector small v in the vector space capital V has exactly one coordinate vector with respect to the basis B. We have already talked about this. On the other hand, it means that for each vector x, that can be written like that here, so these here are the entries, in the vector space Kn, so in this vector space here, there is exactly one small v in the vector space capital V, so that x is the coordinate vector of this particular small v. So for each x in Kn, there exists exactly one small v in the vector space capital V, so that x is the coordinate vector of this particular small v with respect to the basis B. We also have this result here. Two vectors v and w are the same if and only if the coordinates of the two vectors v and w with respect to the basis B are the same. So v is equal to w if and only if the coordinate vectors of v and w with respect to the basis B are the same. Finally, we also have linearity, which means for v and w in the vector space capital V and the value r in the field K, we have that the coordinate vector of v plus r times w with respect to the basis B is equal to the coordinate vector of v with respect to B plus r times the coordinate vector of w with respect to B. Okay, I hope this video helped you to understand the coordinate and basis representation of vectors in a vector space. If you liked this video, please consider subscribing to my channel. It would help and motivate me to keep creating videos.